This video goes through a projection example. So we're given two vectors A and B. Part A is to calculate the scalar projection of B on A. So number one, we're not looking for the vector, we're looking for the scalar projection, which means we're looking for the magnitude. So our formula is going to be the dot product between B and the unit vector of A. So that is just replacing our unit vector of A with A over the magnitude of A. So that means we now have B dot A over the magnitude of A, and B dot A is equal to A dot B. Now our dot product between A and B is equal to -1 times 6 plus 1 times -3 plus -1 times by 2. -6 take 3 take 2 is -11. The magnitude of vector A is equal to the square root of -1 all squared plus 1 squared plus -1 all squared, which is the square root of 3. So our scalar projection is equal to -11 over the square root of 3, rationalising the denominator. That becomes -11 root 3 on 3. And it is a length, it's a magnitude, so I like to put units there. You won't see that in all textbooks. Part B, now we're looking at the vector projection of A on B. So from our formula sheet, the vector projection of A on B is equal to the dot product between A and the unit vector of B times by the unit vector of B. Now the scalar projection of A on B is equal to the dot product between A and the unit vector of B, replacing this unit vector of B with B over the magnitude of B. We get dot product between A and B all over the magnitude of B. Now from part A, the dot product between A and B was equal to -11, and our magnitude of B is equal to the square root of 6 squared plus -3 squared plus 2 squared. So 36 plus 9 is 45, 45 plus 4 is 49, so square root of 49, which is 7. So plugging this in, I have -11 over 7. So my vector projection, which we said was the dot product between A and the unit vector B times by our unit vector B, which equals the dot product between A and the unit vector B times by B over the magnitude of B. So I've just replaced that unit vector of B. So we have -11 over 7 times by B is 6i minus 3j plus 2k, all over the magnitude of B, which is 7. So that becomes -11 over 49, all outside of 6i minus 3j plus 2k. Part C, the vector projection of A perpendicular to B. So let's draw what we're dealing with here. If this is our vector B and this is our vector A, then our projection of A on B is that vector there. And we worked out that that was the dot product between A and the unit vector of B multiplied by our unit vector of B. What we're trying to find is this vector here. So we're going to find do the negative of what we just found plus vector A. Okay, so this here is going to be vector A minus the projection of A on B. All right, so let's work that out. So it equals A minus dot product between A and the unit vector B times by our unit vector of B. Now A is negative I plus J minus K. So that's our A. And then this is from part B. So minus negative 11 over 49 times by 6I minus 3J plus 2K. So let's neaten that up a little bit. Negative I plus J minus K. The minus minus becomes a plus 11 over 49. 6I minus 3J plus 2K. So that equals negative I plus J minus K plus 66 over 49 I minus 33 over 49 J plus 22 over 49 K. So for our I component, we have negative 1 plus 66 over 49. Our J component, 1 minus 33 over 49. And for our K component, negative 1 plus 22 over 49. So that's, and I am doing every single step here, negative 49 plus 66 over 49 for I plus 49 minus 33 over 49 for J plus negative 49 plus 22 over 49 K. So getting that common denominator. Now I'm going to bring out the 1 over 49 and then do the rest. So negative 49 plus 66 is 17I. 49 minus 33 is 16J, and negative 49 plus 22 is negative 27K.